Hi, everyone. We're now going to do confidence intervals for a population variance, sigma squared, or standard deviation, sigma. And we're going to move away from the central limit theorem, the CLT. So here we're going to find 1 minus alpha confidence intervals, again, for either sigma squared or sigma. It's the same theory underlying these two confidence intervals. Basically, remember, for the standard deviation, it's always the square root of the variance. That's the key distinction. Now, again, we're removing ourselves from the CLT. The key assumption here is that the big daddy distribution really has to be normal. So the methods here are not as robust as before. Another term for robust is distribution free. So the CLT was kind of robust in the sense that we were able to apply it to potentially a variety of distributions as the big daddy distribution. But the procedures we're going to do here are not as robust because we really need a big daddy distribution that's about normal, and a large sample size won't help us as much. We need normality. All right, well, here are the formulas for a 1 minus alpha confidence interval for a variance or for a standard deviation. And in these cases, we're going to use a chi-square distribution on n minus 1 degrees of freedom, just like in the t case. Remember, the chi-square, remember there are infinitely many chi-square distributions. We're going to use the one at n minus 1 degrees of freedom, where n is the sample size. Now, here we're going to have different labels because remember, chi-square distributions were never what? Chi-square distributions were never, can I find it? Chi-square distributions were never what? They were never, they were never negative. Chi-square distributions are never negative in value. So there's no plus or minus jazz. No plus or minus jazz. We do have a left critical value and a right critical value. Some comments. So for example, in our example over here, it turns out that this will be chi-square L, the left critical value, and this will be chi-squared R, the right critical value. All right, it's not plus or minus. I have several more comments to make about these formulas. Okay, first off, of course, you don't have to memorize these, but look here. If I were to give you this form for the confidence interval for sigma squared, a population variance, notice that you take the square roots of all three parts to get a confidence interval for sigma, the population standard deviation. So the theory is exactly the same. The underlying theory is exactly the same. We're just recognizing that the standard deviation is always the square root of the variance. So from here to here, you're just taking square roots all the way through. Okay, so if you know this formula, you can figure out this formula. Now notice, unlike before, we don't have symmetry. So for the first time, we don't have symmetry. Before, when we were doing confidence intervals for mu or for p, we had symmetry, and that was a great friend of ours. So critical values could be between, critical values could be of the form plus or minus something, right? Like plus or minus 1.96. But the confidence intervals here for sigma squared or sigma, these are asymmetric. They're not symmetric. So we will not write the confidence intervals in this form. You might think, oh, can I write a confidence interval for sigma squared as s squared, give or take a margin of error? Or something like that for standard dev? No. We do not have symmetry. So you are not going to express confidence intervals for sigma squared or sigma in that kind of a form. In fact, there is no margin of error when you're talking about a confidence interval for sigma or sigma squared. Because, for example, maybe for the variance, maybe s squared is over here. The limits turn out to be here and here. Well, what would the margin of error be, right? We don't have symmetry. Okay. which means we're going to have to explicitly state a lower limit and an upper limit. There's no margin of error. Now notice, unsurprisingly, if you're going to estimate sigma squared or sigma, the sample variance, which is the square of the sample standard deviation, it depends on what you're given, right? If you're given the sample standard deviation S, then square it, all right? If you're given the sample variance, just use it, plug it in here. But it makes sense that these confidence intervals would involve a sample variance or standard deviation. But notice that these formulas do not involve X bar. X bar is not directly a part of these formulas. Now, you could use X bar to calculate the sample variance or standard deviation, but the sample mean itself is not a part of these directly, which actually makes sense because variance and standard deviation are measures of spread. So in principle, the center doesn't really matter. Again, the sample mean could help you calculate S or S squared, but once you get S or S squared, I don't care, right? Like for example, let's say that a class takes a test and the scores are between 0 and 100 points. And we get some sample standard deviation, let's say 5 points. Let's say I'm generous and I say, hey, I'm going to give everybody 10 more points on the exam. Well, the sample mean, or in fact, the population mean will go up by 10 points, but will the spread change? No. The population standard deviation will still be 5 points. You're not changing the spread. Okay, so if I give everyone 10 more points on the test, it changes the center where that is, but doesn't change the spread. Okay, we're going from here to here. We change the center, but not the spread. If I add 10 points to everyone's exam. Not that I'm going to do that. All right. Also, this might confuse you. Wait, why is the right critical value in the left fraction and the left critical value in the right fraction? The greater value is here, the lesser value is here. Well, here's the thing. Let's say that I ask you, I have this pizza here, okay? One person eats a third of the pizza, another person eats a half of the pizza. Who's eating more and who's eating less? The person eating a third of the pizza is eating less, right? Here's a third of the pizza, here's half of the pizza. And the reason is that everything's positive, the tops are the same, okay? But here we're dividing the pizza into 3 pieces, here we're dividing the pizza into halves. So what I'm saying is that because the denominator here is bigger and everything's positive and the tops are the same, because the bottom here is bigger, the overall fraction is smaller. Likewise, this bottom is smaller, so the overall fraction is bigger. In other words, if you believe that 1/3 is less than 1/2, you should believe that this is less than that. All right. Rounding rules. Okay, round off the limits of the confidence intervals to the same number of decimal places as the given value of S squared or S. If we want to be conservative, round out. Round down the lower limit and round up the upper limit, just like before. That will tend to widen the CI a bit. Let's do an example. A 90% confidence interval for a population variance and a population standard deviation. So let's say that, so why would we want to do something like this? Let's say that we have a company that produces pills, hopefully legal pills. And let's say that these pills are supposed to be so many milligrams, right? Like 500 milligrams or whatever. Okay, now if you have pills in a bottle, aren't you going to be worried if one pill looks like that and another pill looks like that? You might be kind of worried, right? Your pill should be fairly consistent because you want consistency, right? In fact, one of the biggest problems in hospitals is problems of dosages, people being given incorrect doses. They're supposed to get 50 cc's of something instead they get 500. So if you have a pill bottle with these different sized pills, you might want to question the manufacturer. Or like Barbie doll heads, right? Here's a Barbie doll body, right? Well, you don't want one head that looks like that, another head that looks like that. All right. So by mass, the pills produced by a company are approximately normally distributed. We need that assumption. Let's say we randomly select 20 pills. So little n is 20. That's the sample size. And therefore, that means we'll have how many degrees of freedom? N minus 1, 19 degrees of freedom. And let's say that based on our Excel spreadsheet, the sample variance is 210 square micrograms. Find a 90% confidence interval, CI, for the population variance, sigma squared, for the mass of the pills. And then later on in part B, we'll do the standard deviation, a confidence interval for the standard deviation. Sigma squared over here in A, sigma over here in B. We'll start with A. All right. Here are some key hints. Here are the critical values from the chi-square distribution. In my Excel spreadsheet, I'll give you this Excel spreadsheet to work things out, but show me your work on the homework. Okay, here's the sample size. I should call this the sample size. Okay, the number of degrees of freedom will be n minus 1, so that's automatic in black. The sample variance, you would input 210 square units. So you enter these two, and also the confidence level, 90% or 0.9. After that, it's going to be automatic. 90% confidence level, alpha is 10%, half of alpha is 5%. All right. So this left critical value cuts off 5% to the left. It turns out the right critical value will cut off the complement, 95% to the left. Okay, so I'm using the CHISQ.inv to get percentiles of a chi-square distribution. Here's the left tail probability, and here's the number of degrees of freedom. I refer to D5 up here. So here's the left critical value. Here's the right critical value. Notice they're both positive, right? Both these critical values will be positive. It's not plus or minus. Again, the probability here is the complement of the probability here, 95% versus 5%. All right, and then we plug these in. Remember that this goes in the right fraction, this goes in the left fraction. Okay, remember we assumed a normal distribution. So our 90% confidence interval, based on this formula, right? N minus 1, which is the number of degrees of freedom, that was 20 minus 1, or 19, times the sample variance, that was 210, over the right critical value. That was the bigger number over to the right, the 30.144. Okay, that goes in the left fraction. And then over here, in the right fraction, we pick the left critical value, the 10.117. That goes over here. The tops are the same. So when you round these limits off, you get 132 square micrograms over to 394 square micrograms. So my Excel spreadsheet, it found that out. If you round these off, 132 to 394. Or if you round out, you round this down to, again, 132, but you would round this up to 395. That's if you want to apply that principle of being conservative, if you're rounding out. But either is fine. I'll accept either. All right. Interpretation, we are 90% confident that this interval contains the population variance of the mass of the pills produced by the company. Regarding standard deviation, we take the square roots of the above. Now, you might be tempted to grab the 132 and either this or this and just take square roots of that, but you're losing too much accuracy. You take the square roots of these guys before they're rounded off. So unfortunately, you got to take these original values. In my Excel spreadsheet, I do that. I refer to these original values. So don't use the rounded off values. Okay, so see, when I work this out, I don't just stick 132 there and 394 or 395 there. Okay, I got to rework it, okay, or get these from memory in your calculator. But yeah, work these out. It's the square roots of the raw left side and raw right sides from above. And this time, for standard deviation, we round off to 12 to 20, or we round out. We can round this down to 11, round this up to 20, all right? So we have either 11 or 12 micrograms, the straight unit, is less than sigma, which is less than 20 micrograms. The lower limit is here, either 12 or 11 micrograms. The upper limit is here, 20 micrograms. You can put this in interval form. We are 90% confident that this interval contains the population standard deviation of the mass of the pills produced by the company. Confidence intervals. Next time, we're going to introduce ideas of hypothesis testing and how we can use confidence intervals to derive conclusions. Next time.